Hello, this is Dr. Hanaa Assil, and this is paper 1C of May-June 2017. This is the Pearson Edexcel International IGCSE Chemistry, paper 1C. Okay, let's discuss the questions. The first question says, the diagram represents an atom of an element. Use numbers from the box to complete the table. You may use each number once, more than once, or not at all. So you have the diagram of an atom. He's showing where is the electron and where is the proton, where is the neutron, and he's asking you what is the atomic number of this atom. Of course, atomic number is number of protons. How many protons do we have? We have 3 protons, so the atomic number is 3. Number of shells shown. How many shells? That means how many energy levels revolving around the nucleus. Of course, you can see that the first energy level has 2 electrons. The second energy level has 1, so you have a total of 2 energy levels or 2 shells. What is the mass number of this atom? How do we get mass number? Mass number is proton plus neutron. So everything inside the nucleus, you have 4 neutrons and 3 protons. So you have a total of 7. That is the mass number. Number of protons in an isotope of this element. Remember that isotopes have the same number of protons. So if this atom has 3 protons, its isotope will also have 3 protons. Remember, an isotope are atoms of the same element having the same number of protons but different number of neutrons. What is the group where the element is found in the periodic table? How do I know which group it is? You should know that the group is the number of electrons in outer shell. It has only 1 electron in its outer shell, so it will be in group 1. Okay, the next question says substances can be classified as elements, compounds, or mixtures. Which of these is the formula for a molecule of an element? So you're looking for 2 things. You're looking for molecule. Molecule means 2 or more atoms joined together. So A is not a molecule, it's an atom. He wants a molecule and it should be an element. Element means all the atoms are the same. So it cannot be C or D, it is B. B shows H2. H2 is the molecule of hydrogen, which is an element. Which of these is a mixture? Okay, let's take a look. Sodium alone is an element. Chlorine alone is an element. Sodium chloride is a compound. The mixture is sodium chloride solution. Which method can be used to separate dyes in a food coloring? Remember, to separate dyes in a food coloring, what do we use? We use chromatography. When do we use crystallization? We use crystallization if we have a solution and I want the solid. So a solution of sodium chloride and I want sodium chloride solid, that's crystallization. Evaporation will do the same thing. You remove the water and you leave the solid. Filtration, when do we use filtration? When we're trying to separate an insoluble solid from a mixture. So, to separate dyes in a food coloring, or to separate sugars, or to separate amino acids, you use chromatography. A student adds a large crystal of sodium chloride to some water in a beaker and leaves the beaker for a day. The diagram shows the beaker immediately after adding the crystal and after 1 day. And the first question is, after a day, the student takes a sample from the top of the liquid and tests it to see if it contains chloride ions, and the test is positive. So he found chloride. Describe how the student should do the test for chloride. What was the test for chloride? You should know the test for chloride is Add dilute nitric acid and silver nitrate. Remember, this was the test for halide, so it is test for chloride, bromide, and iodide. Add dilute nitric acid and silver nitrate solution. With chloride, which we have, we should get a white precipitate. We said before that bromide will give you a cream precipitate. Iodide will give a yellow precipitate. Name the process by which the chloride ions move from the crystal to the top of the liquid. So if I have something at the bottom of the liquid, a crystal at the bottom of the liquid, and it is dissolving, and then the particles are moving from the bottom to the top, that means it is moving from area of high concentration to area of low concentration down the concentration gradient. That is what we call diffusion. So diffusion is movement of particles from area of high concentration to area of low concentration down the concentration gradient. This apparatus is used in a laboratory to separate a mixture of liquids with similar boiling points. So remember, when we're trying to separate a mixture of liquids, then we use this. This is fractional distillation. The passage describes what happens when the apparatus is used. Use words from the box to complete the passage. You may use each word once, more than once, or not at all. So he's saying the mixture of liquids is placed in the what? What is that apparatus where he put the mixture of liquids? In the flask. During heating, part of the mixture boils and passes up that long thing there, that is a fractionating column. So we say that in fractional distillation, you heat the mixture of liquids in a flask, they boil and they go up the fractionating column, and then the water is used to cool the vapor in the condenser so that the fractions come out depending on boiling point. Remember, the one with the lower boiling point is the one that is collected first. Which of these changes of state occurs in the separation? So, which of these is happening? We're not starting with solids. We're starting with liquids, but they're not going to solid. So my answer is C, where we have a liquid. We heat it, it becomes a gas, and then when it goes into the condenser, it changes from gas to liquid. So that is the change that occurs. That is, of course, condensation. The diagram shows 3 pieces of iron. So I have a piece of iron without anything covering it. B has iron with a layer of zinc coated on it, and C has the layer of zinc, but part of it has been removed. So name the process used to coat iron with zinc. Remember that one of the methods to protect iron from rusting is to cover it with a layer of zinc by spraying or dipping. This is called galvanizing or galvanization. The 3 pieces of iron are left in separate troughs of water exposed to the atmosphere for several weeks. The table shows the appearance of the pieces of iron after several weeks. So he's saying A will be covered with brown solid. B is shiny and unchanged. C is shiny and unchanged. The brown solid that covers the iron in A contains what we call hydrated iron 3 oxide. What is the common name for this brown solid? Remember, when we have the iron becoming brown like this, we're saying it is covered with rust. So if he says what is the common name of this brown solid, it is rust. But if he says what is the chemical name for rust, remember, rust is something that happens when iron reacts with water and oxygen. So it becomes hydrated iron 3 oxide. That's the chemical name for rust. Now identify the 2 substances that react with iron to form rust. We said that is water and oxygen. Explain with reference to the symbols in the box why the brown solid does not form on C. Now C was the one that is covered with zinc, and we said so long as the iron is in contact with the zinc, even if a piece of it has been removed, so long as it is in contact with the zinc is more reactive than iron, so it loses electrons and becomes zinc 2 plus. So in that case, this prevents the iron from losing electrons, so the iron cannot become iron 2 plus, and that means it cannot be oxidized, it cannot form rust. Okay? The table shows the formula of some positive and negative ions. It also shows the formula of some compounds. Now complete the table by giving the formula of the 3 missing compounds. Remember we said if we have ions, the number of charges is the same as the valency. So even if I don't know what's the valency of copper, if it has 2 plus, that means the valency of copper is 2. Cl has 1 minus, that means the valency of Cl is 1. And that means if I'm writing the formula, I write the valency of one under the other. So the valency of copper is 2, I put that under the Cl. The valency of Cl is 1, I don't put anything under the copper. Ammonium sulfate, obviously, even without him telling me, I should know that ammonium has a valency of 1, so it has 1 positive charge. Sulfate has a valency of 2, it has 2 negatives, and that means when I write the formula, the ammonium valency 1, I don't write anything under the sulfate, but the sulfate has a valency of 2, so I must put 2 under the ammonium, and that means I must have a bracket to indicate that the 2 applies to nitrogen and hydrogen. So if we put a number below the groups, ammonium, sulfate, carbonate, and so on, you must have a bracket. Now, Fe3 plus with CO3 2 minus, that means the valency of iron is 3, I put that under the carbonate. The valency of carbonate is 2, I put that under the iron. The correct name of the compound with this formula is what? Well, I know that the valency of sulfate is 2, so if I don't put a number under the copper, that means that the copper has the same valency. So first of all, SO4 is sulfate, so A and B are wrong, and copper here has a valency of 2, so this is copper 2 sulfate. Which of these descriptions is correct for ammonium chloride solid, ammonium chloride aqueous? Remember that in both cases, I don't have a transition metal. If I don't have a transition metal, then there is no color. And that means if it is a solid, I say it is white. And if it is a solution, I say it is colorless. We don't refer to it as transparent or white. If it's a solution, it's colorless. These tests are carried out on 2 separate samples of what? Iron 3 sulfate. Now, he's adding sodium hydroxide solution and then dilute hydrochloric acid. Another test is dilute hydrochloric acid and barium chloride solution. So for test 1, he's adding sodium hydroxide to something that has what? It has iron 3. What should I get? I should get a brown precipitate. Remember, sodium hydroxide solution on iron 3 gives a brown precipitate, or we said a reddish brown precipitate. Give the names of the 2 products formed in test 1. What was he doing in test 1? He was adding sodium hydroxide to iron 3 sulfate, and we said that means they will exchange, and that means instead of sodium hydroxide, I have sodium sulfate, and instead of iron 3 sulfate, I will have iron 3 hydroxide. So these are my 2 products. In test 2, there is no visible change after adding dilute hydrochloric acid. Remember, test 2 was where he added dilute hydrochloric acid, then barium chloride. So why are we adding the acid first? We said when we're testing with barium chloride, we have to add acid first to remove any carbonates, because the presence of any carbonates would form a precipitate. even if we don't have what we're testing for. What are we testing for? Remember, barium chloride tests for what? Tests for sulfate. So in test 2, barium sulfate is formed after adding barium chloride. What is the observation that is made? Remember, this is test for sulfate. I add dilute nitric acid and barium nitrate, or dilute hydrochloric acid and barium chloride, and I should get a white precipitate. Describe a test to show that a sample of copper carbonate contains carbonate ions. What is the test for carbonate ions? Remember, carbonate ions is we add dilute acid, so be specific, any acid, dilute hydrochloric acid. When I have carbonate, I should get bubbles of gas that turned lime water milky. Don't say carbon dioxide gas is formed. When we do a test, we want to say what is observed. What do I see? I see bubbles of gas that turn lime water milky. So this is the result of my test. The diagram shows a blast furnace used to extract iron from its ore. I'm going to remind you that to extract iron, I need iron ore, and the iron ore is what we call hematite. We extract it in a huge furnace called the blast furnace, and we react it with coke, limestone, and hot air in the blast furnace. So if he says what are the 4 raw materials that we introduce into the blast furnace, it is the coke, the iron ore, which is hematite, the limestone, and the air or oxygen. So what happens is the first reaction is carbon plus oxygen to give carbon dioxide. And he's saying what is the purpose of this reaction. So when this happens in the blast furnace, you should realize that this is an exothermic reaction. So it helps to raise the temperature of the furnace, so it makes the furnace hot. Then the next reaction that happens in the blast furnace is that we have a lot of coke, so the coke will reduce the carbon dioxide that was formed to form carbon monoxide. And it is the carbon monoxide that reacts with the iron ore. So it is the carbon monoxide that acts as a reducing agent to reduce the hematite. Iron ore contains the impurity silicon dioxide. The purpose of the limestone is to remove this impurity. Remember that the iron ore, which is hematite, we got it from the earth, so the main impurity is sand or soil or whatever we want to call it. Sand in chemistry is silicon dioxide, so silicon dioxide is the chemical name for sand. This is the main impurity in the blast furnace. So the purpose of adding limestone is that the limestone removes this impurity. Now, how does it remove the impurity? The calcium carbonate in the hot furnace breaks down to form calcium oxide plus carbon dioxide. Remember, when something breaks down by heat, this is called thermal decomposition. And then the calcium oxide, which is a basic oxide because it's the oxide of a metal, will react with the silicon dioxide. This is an oxide of a non-metal, so this is acidic. So this second reaction is actually a neutralization reaction. And he's saying write the chemical equation for these reactions. Okay, calcium carbonate to give calcium oxide plus carbon dioxide. And I'm going to remind you again, calcium carbonate is called limestone. The common name is limestone. And calcium oxide, the common name is lime. Now, the calcium oxide reacts with the silicon dioxide, acid plus base to give salt. So this is a neutralization reaction. And this is how we write calcium silicate. Okay? And both of these reactions are already balanced. Otherwise, we should balance it, but they are already balanced. The equation for a reaction that occurs in the blast furnace is this. So the Fe2O3, that is the iron ore that we call the hematite. Now it can react with coke to give iron plus carbon dioxide. Explain with reference to the reactants in this equation why this is a redox reaction. This question is very important. He gives you a reaction, he tells you why it is a redox. Of course, the word redox means what? That it has oxidation and reduction. But you have to specify where is the oxidation and where is the reduction. Now, the carbon has gained oxygen. It changed to carbon dioxide, so it has gained oxygen. When something gains oxygen, that is oxidation. So you have to specify that we're saying it is oxidation because the carbon gained oxygen. Now, the Fe2O3, what happened to it? It became Fe. Okay? Polyethylene is a common polymer. It's obtained from crude oil by fractional distillation, cracking, and polymerization. The passage is about fractional distillation of crude oil. Use words from the box to complete the passage. Again, you may use the word once, more than once, or not at all. Okay, the crude oil is heated so that what occurs? We remember that when we're doing fractional distillation of crude oil, the first thing we do is heat the crude oil so that vaporization occurs. The column has a temperature gradient. Remember that. The column is hot from down in the fractionating column, and as we go up, the temperature decreases so that the ones at the top have lower boiling point. So this is called a temperature gradient, a gradual change in temperature. The compounds in the crude oil pass up the column and something occurs at different heights. Now, what occurs at different heights? Of course, as they go up, they condense at different heights depending on the boiling point of each fraction. They are separated according to difference in boiling points. The one at the top will be collected first. The table lists some statements about cracking. So he's saying place ticks in the boxes to show 3 correct statements. Which of these are correct? The molecules that are cracked are hydrocarbons? Yes. If we say what is cracking, it is the breakdown of hydrocarbons. Catalytic cracking uses iron as the catalyst? No, you should know that the catalyst for cracking is aluminum oxide. Cracking is used because of different demands for hydrocarbons. Yes, we said we do cracking because the ones with smaller molecules or lower number of carbons are more in demand, more flammable, so more economically useful, and so on. Cracking reactions are examples of addition? No. Cracking is not an example of addition, it's an example of thermal decomposition, not addition. Cracking produces molecules with shorter chains, yes. Okay, he's saying this equation is an equation for cracking? No, of course not. Methane plus oxygen to give carbon dioxide and water is equation for complete combustion of methane, not crack. When one molecule of butane is cracked, there are 3 possible reactions. So he's saying this butane can either give me C3H6 plus CH4 or these other products. One product of each of these reactions is an alkene. What is the general formula for alkenes? You have to remember the general formulas. Alkenes, the general formula is CnH2n. That means for an alkene, the number of hydrogens is always twice the number of carbons. What are the names of the products of reaction 1? Where is reaction 1? One of them is C3H6. So this is obviously hydrogen twice the carbon. So this is an alkene with 3 carbons. So this is propene. And then CH4, this is 1 carbon with only single bonds. It follows the general formula of CnH2n plus 2. So that is an alkane. So that is methane. Draw the display formula of the saturated product of reaction 2. What do we mean by saturated? Is he talking about alkane or alkene? Remember, saturated means alkane, means it has only single bonds between carbon, that is saturated. Unsaturated are the alkenes. Unsaturated means it has a double bond between carbon atoms. So which of these is saturated? Which of these is alkane? It is the one that has CnH2n plus 2. So that is the C2H6. What is the C2H6? This is ethane. So this is how we draw ethane. Remember, each carbon must have a total of 4 bonds. The hydrocarbon formed in reaction 3 has 3 isomers. The displayed formula for one of these isomers is this. Now, what is the displayed formula of the other isomers? We're talking about C4H8. So this is butene, and he's telling me to draw the isomer of butene. Butene is something that has 4 carbons. So the double bond in the one he drew up there, it's on the first carbon from the right, and he has a CH3 on the second carbon. Now, to draw an isomer of this, I can draw them all 4 carbons with a double bond on one end, or with a double bond in the middle. Remember, if you take that CH3 and just put it on the last carbon from the left, this is the same as what I drew for isomer 1. Whether you put the CH3 on the same line or bending down at the end of the chain, that is the same. Okay, the reaction used to make polyethene can be represented by this equation. So he has ethene and he's making polyethene, and we said before, if I have the alkene and I'm trying to draw the polymer, we said we copy the 2 carbons that have the double bond, make it a single bond, bond on the right, bond on the left, and then I take a look. Each carbon was bonded to what, and I copy. So that is the polymer. Now he's saying, describe the differences between reactant and product in this reaction. In your answer, you should refer to the carbon chain length, the type of bond, and the state of matter. So let us take a look. The reactant, which is on the left, that is the ethene. It is a smaller molecule. Remember, this is just a molecule that has 2 carbons. It has a double bond between the 2 carbons. And remember that alkanes or alkenes with very small number of carbons, 1 or 2 or 3 or 4 carbons, they are all gases. So alkanes like methane, ethane, propane, butane, these are the alkanes. Alkenes like ethene, propene, butene, these are all gases. What about the product? Well, the product is a longer chain. So remember that we have, in order to form the polymer, we have many of the ethenes joined together in a chain. So it's a long chain with only single bonds. It doesn't have a double bond anymore. He says I should mention the type of bond, so it has single bonds. And we should mention the state. Of course, we know that polymers are basically plastics, so they are all solids. A student uses the reaction between iron and oxygen in an experiment to find the percentage by volume of oxygen in air. And he has this apparatus. State the advantage of using iron powder rather than pieces of iron. Remember, if I'm doing a reaction, instead of using pieces, I should use powdered. Why? Because powdered will make a faster reaction. Remember that the powdered has larger surface area, so the advantage is it will have faster reaction. Why is it necessary for the student to mix the iron powder with water? Remember that what we're doing here is that the iron powder is basically doing rusting. Rusting takes the oxygen from the air, and remember that rusting of iron also needs water. So I need to put water on the iron, and then presence of more water will make the reaction faster, because rusting originally is a slow reaction. Then he says the student records the reading on the syringe at the start of the experiment. He then records the reading every day until there is no further change. The diagram shows the syringe at the start and at the end. Use the readings to complete the table. So the volume reading at start is what? 71. The volume reading at the end is 16, and the change in volume is the difference between them. You can put the minus or not put the minus, that's fine. Remember that when you're filling this kind of tables, please do not put units into the table again. He already wrote centimeter cubed, so don't write 71 centimeter cubed, 16 centimeter cubed, 55 centimeter. No, we don't write the units in the table because it's already written at the beginning of the table. The student repeats the experiment but obtains a much smaller change in volume. Which of these could be a reason for the smaller change in volume? Now, he used much less oxygen. Why do you think he used much less oxygen? Well, if you look at all of this, you will find that it's because he must have used less iron. Because if he used less iron, then that will need less oxygen. During another experiment, the student writes down these values. So, volume of air in the flask and the glass tube is 250. Syringe reading at the start is 90. Syringe reading at the end is 20. So that means that the volume of oxygen is the difference between that, so it is 70. The student incorrectly calculates the percentage by volume of oxygen in air. He's trying to calculate the percent oxygen. What did he do? He put 70 over 90 times 100. Is that correct? Remember that we have, where do we have air? We have air in the conical flask, we have air in the glass tube, and we have air in the syringe. So you don't count only the air in the syringe, you count the total amount of air. So he divided by 90, but the volume of air was 90 plus the air in the flask and the tube. So he should have divided by 340. So use values from the table to correctly calculate the percent. So we're saying to calculate it correctly, I should divide 70, the volume of oxygen, over the total, which is the 340, the 250 plus the 90, times 100. So that is 20.6 or 21%. Hydrogen iodide can be manufactured from its elements using this reaction. So he has a reaction of hydrogen plus iodine to give hydrogen iodide, and the delta H is minus 9. Remember, when the delta H is a negative number, that means that this reaction is what? This reaction is exothermic, and that means when I draw the reaction profile, that means that the reactants lost heat or lost energy. That means that the products will have lower energy than reactants. So this is how we draw the reaction profile for an exothermic reaction. The products should be below the reactants. Now he's saying he did this at a temperature of 500, pressure 4 atm, platinum catalyst, and he's saying on the diagram draw the reaction profile when a catalyst is used. Remember, what is the function of the catalyst? The catalyst speeds up the reaction. Now, if we say, how does it speed up the reaction? That is by lowering the activation energy. So what the catalyst does is, instead of having that high activation energy, it lowers the activation energy so the reaction becomes easier or faster. And he's saying label the diagram to show the enthalpy change. Where is the enthalpy change? You should remember. The enthalpy change is the difference in energy from reactants to products. So remember that the arrow is going down. Where is the energy of activation for the catalyzed reaction? That is from the reactants to the top of that hill or that mountain up there. So that is the energy of activation, and the arrow should be pointing up. A manufacturer carries out this reaction using the same catalyst, pressure 4 atm, but a temperature of 400. So what did he do first? He was doing this reaction at a temperature of 500. Now he's going to repeat it at a temperature of 400. And he's asking, remember that the questions in this case are one of two things. He will either ask you what is the effect on the rate or what is the effect on the yield. Now, if I use a lower temperature, what is the effect on the rate of the reaction? Remember that for any reaction, lower temperature means the rate decreases. What about the effect on the yield of hydrogen iodide? Remember that the reaction, I look at it, the forward is exothermic. That means when we go forward hydrogen plus iodine to give hydrogen iodide, the reaction temperature rises or the reaction becomes hotter. So if I lower the temperature, remember that lowering the temperature of any reversible reaction will cause it to go forward in this case because the forward is exothermic. So in any reaction, lower temperature, it goes exo. Higher temperature, it goes endo. So here we're using lower temperature. That means I will go forward, the equilibrium will shift to the right. That will give more hydrogen iodide, and that means I get a higher yield. Do not forget to mention the effect on the yield and explain why. So we're saying we're going to have more HI, that means I have higher yield. Now, why is that? Because lowering the temperature, it goes exo. Now, which one is exo? It is forward. So that means if I lower the temperature, it will go forward. And that means equilibrium shifts to the right or going forward, and that means it will give more HR. Then he says the manufacturer carries out this reaction using the same catalyst, a temperature of 500, so it's the same temperature, but a pressure of 2 atm. So he's lowering the pressure from 4 to 2. He's using lower pressure. So just what effect this has on the rate? Remember, for any reaction, lowering the pressure, the rate decreases. If I increase the pressure, the particles come nearer, more collisions per second, so the rate increases. So here we're using a lower pressure, rate decreases. Explain the effect of this change on the yield of hydrogen iodide. Now, if we look at that equation, and we're lowering the pressure, what effect would that have? Remember that lower pressure causes the reaction to go to the side with more molecules. Lowering the pressure means you're giving it more volume to work in, so it will go to the side that will give more number of moles. Remember the opposite, if I increase pressure in a reversible reaction, then it goes to the side with less molecules. So here we are decreasing the pressure. What effect? Actually, if you look at this equation, if I go forward, it will form 2 moles of HI. If I go backward, it forms 1 of hydrogen and 1 of iodine, and that means also 2 moles. So if I change the pressure in this reaction, there is no effect on the yield, because the number of moles of reactants and products are the same, so it will not go forward or backward. Okay? Bromine, chlorine, and iodine are elements in group 7 of the periodic table. Place ticks in the boxes to show the 3 correct statements about group 7. Okay. Elements can be obtained by electrolyzing the molten metal halides. So if I do electrolysis of molten, for example, sodium chloride, will I get chlorine? Yes, that is correct. Elements with paler colors are lower down the group. Well, you should remember that these are the halogens, fluorine, chlorine, bromine, iodine, and astatine. As I go down, does the color get paler? No, the color gets darker. The boiling points decrease? No, the boiling point increases because they are gases, liquid, solid. The elements form covalent compounds with other nonmetals. That is correct, because they are nonmetals and they form covalent compounds with other nonmetals. Their molecules contain two atoms. Yes, you know that halogens are diatomic and they should have two atoms. All are gases at room temperature? Of course not. Only fluorine and chlorine are gases. Bromine, we said, is the only liquid nonmetal in the periodic table, and iodine and astatine are salts. Group 7 elements are called halogens because they react with metals to form salts. Write a chemical equation to show the formation of the salt potassium iodide from a metal and a halogen. So if I'm trying to make potassium iodide, which metal should I use? Of course, potassium. Which halogen should I use? Iodine. Remember, iodine is diatomic, so I'm going to write it I2. Potassium iodide. Valency of potassium is 1, valency of iodine is 1, and then we need to balance. Remember that a chemical equation means it is simple and balanced. The equation for the reaction between hydrogen and chlorine is this. At room temperature, hydrogen chloride and hydrochloric acid can both be represented by HCl. So if I write HCl, this could mean hydrogen chloride, and it means hydrogen chloride when we're talking about a gas. So HCl as a gas is called hydrogen chloride. But when I dissolve it in water, it becomes hydrochloric acid, and that is an aqueous solution. So these are the state symbols for each of them. Hydrogen chloride is dissolved in methylbenzene. Methylbenzene is an organic solvent, something other than water. When a piece of magnesium ribbon is added to this solution, there is no reaction. So I'm trying to put a metal to react with it, it doesn't react. When water is added to this mixture and it is shaken, a reaction occurs. So when you have hydrogen chloride dissolved in water and you add magnesium to it, it will react. Now, why is that? Remember that we said hydrogen chloride is unique. When we dissolve it in anything else other than water, so something like methylbenzene, it does not ionize, it does not form hydrochloric acid. So there are no H plus ions, and remember, metals react with acid. So I don't have an acid, so there is no reaction with the metal. But if I put it in water, then the hydrogen chloride ionizes to form hydrochloric acid. That means the solution is now acidic with H plus ions. Now the magnesium can react with the acid, and that helps to form bubbles of hydrogen gas. Halogens can take part in displacement reactions with halides. The table gives information about the addition of halogen solutions to halide solutions. So he's adding bromine to sodium iodide. It reacts. Chlorine to sodium chloride, no reaction. Iodine to sodium chloride, no reaction. Now explain which test gives a result that cannot be used to compare the reactivities of halogens. Which of this is a result that I really don't use? You should realize that test 2, when he added chlorine to sodium chloride, well, anyway, you're not going to have any reaction in that because chlorine cannot displace itself. Chlorine cannot react with chloride. Which observation shows that a displacement reaction occurs in test 1? This is test 1. Test 1, he said bromine with sodium iodide, and he got a reaction. So what do you think he got? Well, he's reacting what? He's reacting bromine with sodium iodide. So this will give sodium bromide plus iodine. And when we have iodine in solution, that means the solution becomes darker. Remember, sodium iodide solution does not have any color. It's not a transition metal, so it's a colorless solution. But when it forms iodine, iodine in solution forms a brown solution, so the solution becomes dark. Astatine is an element in group 7 that could also be involved in displacement reactions. The ionic half equations for one of these reactions is this. Write an ionic equation for this reaction. Remember, when he gives you half equations means in order to get the total reaction, you just add up these two reactions. But when we add them up, we have to cancel the electrons on both sides of the arrow. And in order to cancel them, they have to be the same number of electrons. So if I have 2 electrons before the arrow, 2 electrons after the arrow, we cancel that and we add up what is left. So before the arrow, what do I now have? I have chlorine and 280 minus. What do I have after the arrow? I have 2Cl minus and 82. So this is my net reaction or my overall reaction. Explain with reference to the species and to electrons why this reaction is described as a redox reaction. Again, this reaction, why do we say it's a redox? You're going to explain to me that this involves chlorine gaining electrons, and gain of electrons is reduction. The 80 minus loses electrons, and loss of electrons is oxidation. So because we have oxidation and reduction, then this is a redox reaction. But you have to be specific. Don't just say it has oxidation and reduction. Well, where is the oxidation? Where is the reduction? And if we say chlorine was oxidized or reduced, chlorine was reduced in this case, why do we say it was reduced? You should say that is because it is gaining electrons, so that is reduction. The other one is losing electrons, and that is oxidation. This question is about magnesium and its compounds. A student draws this label diagram to show the particles in magnesium metal. So look at the diagram. He says he makes 2 mistakes. State the 2 corrections he should make to his label diagram. What is wrong with his label diagram? Of course, when he says delocalized protons, that's wrong. If we're drawing the diagram of a metal, we say the metal has delocalized electrons, not protons. And then this regular rows of ions that he has, one of them positive, negative, that's not right. All the ions should be positive ions. Remember, we write positive, negative when we're talking about an ionic compound, not a metal. Metals have regular rows of positive ions, so all the ions should be positive. Explain why magnesium metal is malleable and a good conductor of electricity. So this is the diagram of a metal. Why do we say that metals are malleable? Remember, if I say describe the structure of a metal, we said a metal has what? Regular rows of positive ions surrounded by a sea of delocalized electrons. Now, why is it malleable? We say it's malleable because the layers of positive ions can slide over each other when heated or hot. Why is it a good conductor of electricity? Because it has free-moving, delocalized electrons. Please remember to mention that it has delocalized electrons that are free to move. Okay? Magnesium is a reactive metal. Its reactivity can be seen in its reactions with oxygen and dilute sulfuric acid. So in reaction 1, some magnesium is ignited, placed in a jar of oxygen gas. State 2 observations that would be made. You should know that when we burn magnesium in oxygen, what do we see? We see that the magnesium burns with a bright flame, and the magnesium oxide that is formed is what we call a white solid or white ash. So what are the observations? That the magnesium burns with a bright flame, or you could say a white flame, and a white solid is formed, or white ash is formed. Which of these is a correct statement about the gas formed in reaction 2? Of course, when you look at reaction 2, which gas is formed? Hydrogen. What can we say about hydrogen? Of course, if you remember the test for hydrogen, it makes a squeaky pop with a lighted splint. Which gas relights a glowing splint? Relights a glowing splint, that's talking about oxygen. Turns damp blue litmus to red. Well, turns damp blue litmus to red, that's any acid actually. Turns lime water milky. Which gas turns lime water milky? That is carbon dioxide. So hydrogen, it makes a squeaky pop with a lighted splint. Reaction 2 was this. The student used this method to obtain a sample of magnesium sulfate crystals. So he's trying to make magnesium sulfate crystals. Heat the solution in a beaker. So he already added magnesium sulfuric acid. Heat the solution in a beaker for several minutes. Dip a glass rod into the hot solution for a few seconds and then remove it. Allow the solution to cool at room temperature. Filter off the crystals and then dry them. So what is he doing? He has already added magnesium to sulfuric acid and he has the solution from that. So the solution is the magnesium sulfate solution. And what is he doing? He's trying to do crystallization, right? So why does the student heat the solution? Remember, when we're doing crystallization, we say heat the solution to point of crystallization. So why is he heating it? To remove some of the water to reach point of crystallization. Then he's saying he's dipping a glass rod and remove it. Why do we dip a glass rod and remove it? To determine if crystals form, to indicate that the solution has reached point of crystallization. Remember, if he says, how do we know we have reached point of crystallization? We tell him, insert a glass rod and remove it. Crystals should form on the tip. Do we understand that? So basically, he's doing crystallization. Now, give the formula of the two compounds that pass through the filter paper. Because what we have in the solution would be the magnesium sulfate and the water. Remember, the hydrogen gas has already escaped. After drying the crystals, the student weighs them and then heats them until they reach a constant mass. So he has magnesium sulfate X water, and basically he's trying to find out what is X. So these are the student's results. The mass of the crystals before heating, that means the mass of all of it, magnesium sulfate X water, is 17.2 grams. The mass of the crystals after heating, and that means the mass of the magnesium sulfate after we have removed all the water, is 8.3 grams. Use these results to find X. How do we do that? So he has removed all the water and the mass of the magnesium sulfate is 8.3. But what would be the mass of the water? The mass of the water is the difference between the initial mass of the hydrated crystals and the final mass of magnesium sulfate. So that means I have 8.9 grams of water. Now we do it as if we're doing empirical formula. We say we have 8.3 grams of magnesium sulfate. We have 8.9 grams of water. How do we do empirical formula? We divide first by the molecular mass of each one. He already gives me, please notice, so you don't need to sit down and waste time trying to calculate the MR. He already gives me what comes out. I look at the numbers, I divide by the smallest. So this is the smallest. So this is 1 to 7. That means that my X is 7, and that means the formula was magnesium sulfate, 7 water. This question is about calcium compounds. The diagram gives information about the reactions of some calcium compounds used to make mortar. Mortar is something like cement. Mortar contains calcium hydroxide and is used to join bricks together when building walls. These reactions occur when the calcium hydroxide in the mortar is obtained from calcium carbonate. So we're trying to get the calcium hydroxide, so he's heating calcium carbonate to form calcium oxide, and then water is added to the calcium oxide to form calcium hydroxide. The calcium hydroxide in the mortar reacts with carbon dioxide from the atmosphere to form calcium carbonate. So these are the basic reactions he's talking about. Now, what is he asking? The equation for one of these reactions is this. Calculate the mass of water needed to react exactly with 28 kilograms of calcium oxide. So he's giving me information about calcium oxide. He says the mass is 28 kilograms. And he's asking for mass of water. So what should we do first? Calculate the number of moles of what he gives me. So he's saying I have 28 kilograms of calcium oxide. Number of moles would be the mass over the molecular mass of calcium oxide. That means I have 500 moles of calcium oxide. Then I look at the equation. What is he asking about? He's asking about water. And from the equation, 1 mole of calcium oxide reacts with 1 mole of water. So the number of moles of the water would be the same as the number of moles of calcium oxide. So now I have number of moles of water. He wants what? He wants the mass. Mass is number of moles times mR. Remember, in all of these reactions, we're using the mass in grams, not kilogram. So the 28 kilogram at the beginning, we multiply by 1,000, and that is why we got 500 moles. And here, mass of water is number of moles times mR. What comes out is in grams. So if he wants it in kilograms, you divide by 1,000. Explain why the reaction between carbon dioxide and calcium hydroxide can be described as neutralization reaction. You should remember, what is neutralization reaction? It's reaction between an acid and a base. So which of these is acid and which one is a base? Of course, you should realize that carbon dioxide is acidic. This is the oxide of a nonmetal, so it's acidic. And calcium hydroxide is a base, so acid plus base to give salt plus water. That is a neutralization reaction. Calcium carbide is a reactive solid. When water is added to it, a gas called ethine is formed. A teacher uses this apparatus to investigate the rate of reaction between calcium carbide and water. This is the teacher's method. Record the temperature of the water in the flask, add a known mass of calcium carbide, replace the bung, record the time taken to collect 100 centimeter cubed of gas in the syringe. The teacher repeats the experiment using the same volume of water, same mass of calcium carbide, but with water at different temperatures. So basically, he's trying to get the effect of different temperatures on the rate. He got this results and he's asking us to plot the results on the grid and draw a curve of best fit. So he already wrote everything. He already labeled the axis. Remember that whatever is on the top of the table here should go down. So temperature of water in degrees Celsius is the one on the x-axis. Time to collect 100 centimeter cubed of gas in seconds is on the y-axis. And he already divided everything for us. All we need to do is just plot. Please be careful when plotting. He follows point by point as an examiner, and any mistake in one of the points, you lose one of these 3 marks. Then he's saying draw a curve of best fit. So you join it, trying to take in all of the points in a curve. Then he says the teacher plots this graph to show how the rate of reaction varies with temperature. So here he's talking about rate versus temperature. And her graph shows that the rate of reaction is not directly proportional to temperature. There are 2 reasons why the rate of reaction increases as the temperature increases. You should know that when I increase the temperature, the rate increases. One reason is that the water molecules move more quickly, collide more frequently with the calcium carbide particles. Explain the other reason for the increase in rate of reaction. Remember, when we increase temperature, why does the rate increase? You should know that that is because the particles will gain more kinetic energy. So more particles have energy higher than energy of activation. Remember we said energy of activation is the minimum amount of energy needed for a reaction to occur. So if more particles have higher energy, more particles have energy higher than the energy of activation, then there will be more successful collisions per second. And that is why increasing temperature will increase the rate. And that was the last question in this paper. I hope this was not too long for you. Remember, this paper is actually a 2-hour paper. You should do it in 2 hours. So this is the longer paper. I hope this was clear to you and useful, and please share it with others if you can, so that as many students as possible can benefit from it. Thank you for listening.